Ah, test, test. Ah, test, test. Ah, test, test. Test, test. Test, test. Ah, hello, hello. That's so quiet. Ah, uh, hello? Uh, 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 hello?
Hello?
Test,
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 test.
test.
Hello?
Hello? Test, test, test. Test, test, test. Ah. Test, test, test. Ah. Test, test, test. What's what I'm trying to... test. Test. This is something on channel 2, bruh. This is something on channel 2, bruh.
There's a noise. Test. Hello? Test. Hey, what's up? 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 Test. Hey,
Hello, everybody. If you recall from last class, we looked at the equilibrium constant, and we said that the equilibrium constant allows us to be more quantitative in our treatment of chemical equilibrium. And we said that the equilibrium constant is given by the equilibrium expression, or the law of mass action, which gives us the ratio of the concentration of products raised to the power of their coefficients to the concentrations of reactants raised to the power of their coefficients. Simply put, the equilibrium constant gives us the amount of products. It gives us the ratio of the amount of products to reactants. Okay? So today, we're going to move on to looking at the fact that only in the case of gases, the equilibrium constant can be expressed not only in concentration, but it can also be expressed in terms of the partial pressure of the gases. So let's look at why only in the case of gases we can express the equilibrium constant in terms of the partial pressure of gases too. Okay, so in the case of gas, the pressure exerted by gas and the volume of that gas and the number of moles of that gas and the Kelvin temperature are related by the equation PV equals nRT. And if we take the PV equals nRT relationship and now rearrange it so that we take the volume from the left-hand side to the right-hand side, you can see that it now becomes the denominator. And when we rearrange this equation, it looks like this, where if we isolate N divided by V. Remember, N is the moles of a gas in a mixture of gases. V is the volume of the container. And we know that when you take the moles of a gas in a mixture of gases and divide by the volume, you get the concentration in molarity of that gas. So this gives us molarity, and we know that the unit is moles per liter. And so we can go back to this equation and we can replace N over V with M, which represents the molarity or the concentration of that gas. Because if we're at constant temperature and R is a constant, we can say that this now equals pressure equals molarity times a constant K, let's say constant K. And because this is a constant, we can say now that pressure is directly proportional to molarity as given here. So we can say that the pressure of a gas is directly proportional to molarity. When you have mixtures of gases, we know that the pressure exerted by each individual gas is called the partial pressure of the gas. And so the partial pressure of a gas in a mixture of gases is directly proportional to the concentration in molarity. Okay, so now that we know that the concentration of a gas in a mixture of gases is related to the pressure exerted by that individual gas, which is called the partial pressure, now we can derive an expression to express the equilibrium constant in terms of partial pressures. Okay, so let's start with this example. And if you look at this example, this is a homogeneous equilibrium, and you can see that the reactants and products are all gases. And if we wanted to express the equilibrium constant in terms of concentrations, we can say K. By default, the equilibrium constant is always given in concentrations. So we can say K, or if you want to kind of specifically remind yourself that this is in terms of concentrations in molarity, we put a subscript C as a reminder that we're going to, for this gas mixture, we're going to express it in terms of units of concentration. So we can say that the law of mass action, or the chemical equilibrium expression, can be given as the concentrations of the products raised to the power of the coefficient divided by the concentrations of each reactant raised to the power of their coefficient. And this would be the equilibrium expression in terms of concentration. If we want to determine the unit for the equilibrium constant in terms of concentration, we can say that the products will be molarity squared divided by molarity times molarity raised to the power 3, and you can see now this becomes molarity to the -2. So this would be sort of the traditional way in which we would express the equilibrium constant, and the unit for the equilibrium constant will turn out to be molarity to the -2. Because this has a mixture of gases, we can now also express this as an equilibrium constant, but now in terms of the partial pressure exerted by the mixture of the gases of reactants and products. So we're going to express them in terms of pressure. Now we're going to say it is Kp to remind us, the subscript P reminds us that we are looking at this equilibrium constant in terms of partial pressures. Now we're going to express this in terms of partial pressure. We know concentrations and partial pressures are directly proportional to each other. And so now we can say that the partial pressure exerted by the products raised to the power of their coefficient divided by the partial pressure of the reactants raised to the power of their coefficients. And because the unit that we use for partial pressure is traditionally atmospheres, we're going to express them in terms of atmospheres squared over atmospheres, and this would be atmospheres raised to the power 3. So if we were to express the equilibrium constant in terms of the partial pressures of the mixtures of gases, and in this particular instance, if we express them all in atmospheres, our answer will come out to be in units of atmospheres to the -2. So only in the case of gases, we can express them in terms of K or Kc, or in terms of Kp. But because these are two sets of different units, the numerical value of these two values will be different. okay? And just to remind you that we usually express partial pressures like this. As a subscript, we indicate the species that exerts that partial pressure. And so when we say P subscript NH3, it is the partial of NH3. P subscript N2 will be the partial pressure of N2, and P subscript H2 will be the partial pressure exerted by H2. So in the end, only in the case of mixtures of gases where your reactants and products are gases, we can express the equilibrium constant in two different ways. And we said that depending on whether we pick concentration terms or whether we pick partial pressure terms, these two constants will have different numerical values and different units, okay? Now, it is also important for us to be able to relate the two. Remember, only in the cases of gases, we can express them in terms of Kp, and we can express them in terms of Kc. But we should also be able to mathematically convert one to the other. So if we're given Kc, can we figure out the corresponding Kp? And vice versa, if you are given Kp, can we figure out the corresponding Kc? All right? In order to do this, let's take the general form of the reaction where we have two reactants giving us two products. Hello, everybody. If you recall from last
His name is Francisco, right?
The gay one.
What? Greg's roommate's name Francisco.
Yeah. Wait. Would you used to think his name was Carlos?
Yeah. That's racist. I'm about to cut his name.
Carlos?
Okay. Dude, if you say that, I'm actually gonna end up on Carlos. Don't do that. That's bad. Dude, the whole, I think first quarter, I thought that was his name. You know, I didn't know his name.
Yeah, Carlos. Remember, don't forget Carlos. Carlos. Don't forget Carlos, bro. Oh, you have the chat? Yeah. Yeah.
Okay, streamers.
The streamer house, bro.
We made a streamer house.
When's Oliver gonna stream, bruh?
He streamed last night.
Actually?
Yeah.
Oh.
Ask your vintage to be only $20. These jokes. That's what I'm saying. We can set up an auction for your hat. I'll take 25% of the cut.
Bro, me and Udi were just gonna go on a walk on the trail, right? And we ended up, we walked for heck along to the point that we were by Fashion Island. So we just went there, and then after that we bussed back, and then after that,
Correct.
Theory 4.
Please be.
While you were doing that, we had work.
Oh, pregnancy test. Oh my god, we got pregnancy test, guys. 2 nubbies, which means we're gonna pivot. We're pivoting to a nubby die build.
Wait. Bro, I think it's a little bit big, bro. Bro, I think it's a little bit big, bro.
Large.
I think I'm gonna get an XL.
Yeah. I think it's just a large next time.
I think I'm gonna get an XL next time.
I got a small one.
Huh?
I got a small one.
No, but remember it's different.
Huh?
Yeah. You get. No, but remember it's different. I think I'm gonna get an XL. It's not that it's like. I think I'm gonna get an XL. It's not that it's like. too long.
Check chat, bro.
Huh?
Check chat.
Check chat?
It's chat.
You're a bully, bro.
Hello, everyone. Today, I'm going to pick up where we stopped last time. If you recall from the last lecture, we started looking at chemical kinetics, and we said chemical kinetics is the study of how fast reactions.
You know you can connect your MacBook to your thing. I don't stream MacBook camera as your camera. I'm the master of this room.
What's up guys, take care. Streamline screen over here. Now you have to do it.
Taxes was
Oh, mine doesn't. That's why that's why I have a hub. That's why. I have an extra hub if you want. Alright. You have to face it. I'm so smart. You know? I walked for 9 months. I feel like after I cut. Oh yeah, I'll see you. Oh yeah. Okay. After this,
Because I keep forgetting. They keep finding me. It's fine. Just like,
I keep forgetting something. Like, yeah, I know.
it's Irvine. They charge like 40
I already
bucks.
said yes to him. I don't want to say right now. Well, I'm probably just gonna do something light because I don't have a lot of time right now. So I'm going to start eating. I'll be walking. More? Huh? More walking? I need more cardio, bro.
Hey, Mark.
9 miles.
It's you.
What? What is this? Let me see. Hey, let's go. It looks like I'm part of the game. Yeah.
Yeah.
Hey.
Let's see if they sent you any affirmations.
Unless you're like right now, like I'm tired, but I want to. You won't be able to sleep. No, you won't. If you did get past 3 p.m. or 4, or even 5, even just a step, I don't think so. I think it's gonna be too much, and that's too late. Really? Yes. Even just like a tiny little step, you still won't be able to sleep. I think you will actually. You want a tiny step? Literally, like, start jumping jacks right now. You won't be tired. Go, 1, 2. I just ate. I literally just ate. Then why don't you want to go to the gym? I don't know. Think about this. Tiredness is just a mindset. It's literally just a mindset. It's just a mindset. Wanting to nap is just a mindset. No, just go downstairs. No, I want to squat. See, if you have like such a big goal to the point that it's like a little bit too much, it ends up making it not what it is. But if you're just like, oh, I'm gonna just go to the gym, even just for 10 minutes, it's much easier, right? Yeah. But come on, you want that body for summer? Let's go. Yes.
I'm following, bro.
Chat, cancel him, chat.
I am chat.
I am chat.
I am chat.
I'm the only chat.
I am Steve.
Chicken jockey. Go fish and scuba water.
Have you seen the another?
Where they said fireworks off instead of
Oh yeah.
That was fake. That wasn't actually.
But you
I
saw
saw it though. It's like Mad Max.
Mm.
Why did they set off the fireworks?
I don't know. The thing was gonna be on fire. The whole theater.
Yeah, I saw. Bro, people were running out of the theater.
Chicken monkey.
Hey, someone's about to buy my iPad. Really? We're gonna meet up today.
Cool.
Is she a baddie? Yeah. She looks like she already graduated and stuff. Yeah. He's just a number one. Don't let these conceptual boundaries down you. I'm pretty sure that.
If you want to take your communication to the next level, whether you're running a business or just starting out, Grammarly has you covered. Grammarly
will guide you through and green. You can go and see the pricing, and then I'm going to keep using the free trial. And then what you need to do is make sure you unblock it. I'll just press fix it like this, and then it should go and sort.
She's on top of the world, it's a good life. I get up just as high on a good night, and it's good, right? She wants flowers to grow in the sunshine, but I run just like the wind in the moonlight, and it's not right, 'cause in my mind she's a dream. The best thing that happened to me. She's a dream, all that I thought it could be. She's a dream come true, but I have nightmares. It should have been you. You were all that I had for a long time, and I still think back to you on a bad night. I thought that I was dreaming when you said you loved me. The start of nothing, I had no chance to prepare, I couldn't see you coming. The start of nothing, ooh, I could hate you now. It's quite alright to hate me now, when we both know that deep down, the feeling still deep down is good. If I could see through walls, I could see it faking. If you could see my thoughts, you would see our faces. Safe in my rental, like an army truck. Back then, we didn't give a fuck. Back then, I ain't a kid no more. We'll never be those kids again. We tried to six, had the X6 back then. Back then, no matter what I did, my waves wouldn't dip back then. Everything sucked back then, we were friends. I thought that I was dreaming when you said you loved me. The start of nothing, I had no chance to prepare, I couldn't see you coming. The start of nothing, ooh, I could hate you now. It's quite alright to hate me now, but we both know that deep down, the feeling still deep down is good. In the halls of your hotel, arm around my shoulder so I can tell how much I'm into you, meant to
and the detailed events that take place as reactants convert to products. And so we said that we're interested in looking at how fast reactions proceed, and the term that we use to describe how fast a reaction proceeds is called rate. And we defined rate as the change in concentration of either reactants or products as a
The start of nothing, had no chance to prepare, couldn't see you coming. And we started from nothing. Ooh, I couldn't you now. It's alright to hate me now. We both know that deep down, the feeling still deep down is good. All the things I didn't mean to say, I didn't mean to do. There were things you didn't need to say. Did you need to?
function of time. And we looked at two rates, the average rate and the instantaneous rate, and we talked about the fact that we are most interested in instantaneous rate. We also looked at the fact that when we look at the rate of a reaction, the rate of the reaction is the fastest the instant the reaction starts, and as the reaction proceeds, we see that the rate of that reaction slows down. And then we're going to try to figure out the exact form of the rate law. So if we write the general form of the rate law, we can say rate equals K. We have only one reactant, which is HI, so the concentration of HI raised to the power n. In the end, if you look at this equation, experimentally, in each instance, we have 3 trials where we have the rate and concentration. So we know the rate and concentration. What we don't know is the value of the rate constant K and the value of the order with respect to HI, which is n. So as all of you know, in the end, we need to establish what the order is, which is n, and we need to establish the value of K. So this is the general form of the equation. As you can see, this is an equation where there are 2 unknowns. And in math, we know that if you have 2 unknowns, then in order to solve for the 2 unknowns, we need 2 equations. So we need to write 2 equations so that we can determine the value of n and the value of k. So in order to do that, we're going to go to the 2 trials. The first 2 trials, we can take any. You can take the first 2 trials, you can take the second and the third, or the first and the third. We're going to take the data from 2 sets of trials, and we're going to put the values into this equation. So we'll start with the first trial data, which is 1. We know the rate is 7.5, that this is the number that corresponds to this, 7.5 times 10 to the negative 4 moles per liter per second, that's the unit for rate, equals a constant k times the concentration of HI raised to the power n. So now we've taken this general form of the equation and we put the values that correspond to rate and concentration to the equation. So this is the equation that corresponds to the data from the first trial. We're going to take the data from the second trial and put it in here. So the rate is 3 times 10 to the negative 3 moles per liter per second equals the rate constant times 0.010 moles per liter per second raised to the power n. So now we have 2 equations and 2 unknowns, and we need to solve for it. In order to do that, the strategy that we're going to use is we're going to take one of these equations and divide by the other. Now, as a rule of thumb, it is a good idea to always take a larger number and divide by a smaller number, because whenever you take a large number and divide by a small number, you always end up with a whole number. If you were to take a small number and divide by a large number, you'd end up with a fraction. Sometimes the math is hard. So let's pick between these two. Let's pick the one that has the higher value, which is 3 times 10 to the negative 3. So I'm going to take equation 2 and write down equation 2, and I'm going to divide equation 2 by equation 1. Now, when you do that, you can see that now when you divide one equation by the other, k and k will cancel out. Also, you'll notice that the units will cancel out. This unit, moles per liter per second, and moles per liter per second will cancel out. And you can see that moles per liter and moles per liter will cancel out.
Concentration. In this video, we're going to talk about how to solve integrated rate law problems. So if you have a pen and a sheet of paper with you, feel free to use them to take down some notes, which is going to be useful later on as we work on some problems in this video. So let's begin our discussion with the rate law expression for each of these ordered reactions. So for a zero order reaction, the rate is equal to K times A raised to the 0 power. Anything raised to the 0 power is 1. So the rate is simply equal to K. A is a reactant. So think of a reaction where, let's say, A turns into B. So A is the reactant and B is the product. So for a zero order reaction, the rate of the reaction doesn't depend on the concentration of the reactant. For first order reaction, the rate does depend on the concentration of the reactant. Its rate is equal to K times A raised to the first power. For a second order reaction, the rate is equal to K times A raised to the second power. So the order of the reaction is based on the exponent that you see here. Now, for a first order reaction, if you double the concentration of A, the rate is going to double. If you triple the concentration of A, the rate is going to triple. For a zero order reaction, if you double the concentration of A, it's going to have no effect on the rate. If you triple the concentration of the reactant A, no effect. 3 to the 0 power is 1. For a second order reaction, if you double the concentration of A, 2 squared is 4. The rate is going to increase by a factor of 4. If you triple the concentration of A, 3 squared is 9. The rate is going to increase by a factor of 9. So the order of the reaction, or rather the order of the reactant, tells you how the concentration will affect the rate. The rate of the chemical reaction is most affected by a reactant that is second order compared to a reactant that is first order or even zero order. So the higher the order of the reactant, the greater its impact will be on the rate of the reaction. Now let's talk about the units of the rate constant K. So the units of K for a zero order reaction is going to be m to the first power times t raised to the negative 1. Now, t is a unit of time. It could be seconds, it could be minutes, it could be hours, it could be even days. But t is some type of unit of time. Now, for a first order reaction, it's going to be m to the 0, t to the negative 1. Or simply, t to the minus 1. For a second order reaction, the units of K is going to be m to the negative 1, t to the negative 1. And notice what's happening to the exponent of m as you increase the order of the reactant. It's decreasing by 1. So for a third order reactant, it's going to be, the units of K will be m to the negative 2, t to the minus 1. So we can come up with a general equation that will tell us the units of K given the order of the reaction. And here it is. It's m raised to the 1 minus n times t to the negative 1. So that's the units for K for any order. So let's say if it's second order, n is 2. So this is going to be m raised to the 1 minus 2 times t to the negative 1. 1 minus 2 is negative 1, so you get this. So this expression is very useful in determining the units of K given the overall order of the reaction. Now the next topic of discussion is the half-life. So the half-life is a unit of time. So it's going to be t with a subscript 1/2. And that's the time it takes for the concentration of a reactant to decrease by half of its original amount. For a zero order reaction, the half-life is going to be the concentration, let me write this better. It's going to be the concentration of A, more specifically the initial concentration of A, divided by 2K. For a first order reaction, the half-life is going to be ln2 divided by K, where K is the rate constant. And for a second order reaction, it's going to be 1 over K times the initial concentration. So what you want to gather from this is that the half-life for a first order reaction doesn't depend on the initial concentration. For a zero order reaction and a second order reaction, the half-life depends on the initial concentration. But for a first order reaction, it's independent of the initial concentration. Make sure you write that in your notes too, because that's a typical test question. Now in all cases, the half-life, because that's a but for a first order reaction, and a second order reaction doesn't depend on the initial concentration. From this is that the half-life for a first order reaction doesn't depend on the initial concentration. For a zero order reaction and a second order reaction, the half-life depends on the initial concentration. But for a first order reaction, it's independent of the initial concentration. Make sure you write that in your notes too, because that's a typical test question. Now in all cases, the half-life depends on the rate constant K. And notice that K is always in the bottom of the fraction for the half-life equation. So that means for all cases, as the rate
Test.
I'm sure we're taller in other dimension. You say we're small and not worth the mention. You're tired of moving, your body's aching. We could vacate, there's places to go. Clearly this isn't all that there is. Can't take what's been given. We're so
Test.
okay.
Hello?
It's just a skull, at least that's what they call it, and we're free to fall.
Constant increases, the half-life will decrease, regardless of the order of the reaction, if it's zero, first, or second order. Regardless, that means for all cases, as the rate constant increases, the half-life will decrease, regardless of the order of the reaction, if it's zero, first, or second order.
Oh, you got power, superpowers. Do you even know how to wield them? All God's children are special, but not like you. No, not like you. You're just like a flower. You're ever giving. That's a given. All God's children are special, but not like you.
Hello, everybody. Today, we take place with chemical reaction is this liquids a solvent H2 raised to the power 2, the product raised to the power of its coefficient, times
It's crazy to say this, but you're the greatest.
Hello, everybody. Today, we're going to finish up chemical kinetics, and we're going to look at factors that affect the rate of a reaction. One factor that we already know that affects the rate of a chemical reaction is the concentration of its reactants. After all, that's what the rate law gives us. The rate law gives us the dependence of rate on the concentration of the reactants. The second factor that influences how fast a reaction takes place is temperature. As you increase the temperature, the rate of a reaction increases. And the general rule of thumb is for every 10 degrees centigrade increment in temperature, the rate of the reaction doubles. Now, the reason
Test, test, test. 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 Test, test, test. Hello, hello, hello. Ta 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 ra 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 ta 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 ta. Hello, 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 hello. Test, test. Oh, it works. Okay. I don't know if it sounds good or not, but hopefully it sounds good enough. Maybe I should lower this. Test. Hello, hello. Test, test. Hello, hello. Okay, okay. Can you check my stream now? I hope my thing works now. I really hope my thing works. As my head hurts.
Oh, my head hurts too.
Okay, can you check my video?
That the rate increases with temperature is because as you raise the temperature, the kinetic energy of the reactant molecules increase. And as the kinetic energy of the reactant molecules increase, they're going to move a lot faster. And the faster they move, the more frequent they can collide with each other. And the more frequent they can collide with each other, the rate of the reaction increases. Remember when we looked at each elementary step in a reaction mechanism, we said that each elementary step requires molecules to collide with each other. And so the more frequently they collide with each other, the faster the reaction will take place. Okay? Now, both temperature and concentration affect how fast the reaction takes place because they're both affected by the frequency of collisions. If you raise either temperature or concentration, you increase the frequency of collisions, and therefore the reaction proceeds a lot faster. In the case of concentration,
All my iPod screen protectors up.
Here. Right, device printers. So what they do for you is they give you the property. Okay, alright. Huh? Ah.
You know taxes are due in a few days.
Yeah.
Make sure to file the taxes.
Am I supposed to?
if you made big purchases, or not big, if you sold sold stuff for big purchases.
Like how much?
I don't know. I just know you have to file taxes if you make if you sell something really big. Like you sell something for $1,000, something like that. But technically, I don't think you have to because I doubt you sold anything like
what?
like paperwork wise.
Yeah.
So I think hopefully I did my taxes correctly.
And what we end up with is if I take this term and divide it by this term, it comes out to be 4. If I look at this term, it is 0.05 raised to the power n. This is 0.01 raised to the power n. If I divide this by this, it is 2, and that would be equal to 2 raised to the power n. To that equation. So this is the equation that corresponds to the data from the first trial. We're going to take the data from the second trial and put it in here. So the rate is 3 times 10 to the negative 3 moles per liter per second equals the rate constant times 0.010 second raised to the power n. So now we have 2 equations and 2 unknowns, and we need to solve for it. In order to do that, the strategy that we're going to use is we're going to take one of the other. Now, as a rule of thumb, it is a good idea to always take a larger number and divide by a smaller number, because whenever you take a larger number and divide by a small number, you always end up with a whole number. If you were to take a small number and divide by a larger number, you end up with a fraction. Sometimes the math is harder. So let's pick between these two. Let's pick the one that has the higher value, which is
anymore. Audio input capture. I think that's me talking. So I can't hear any desktop audio. And I can't hear any desktop audio either. Why can't I hear anything? Why can't I hear anything?
That's 10 to the negative 3. So I'm going to take equation 2 and write out equation 2, and I'm going to divide equation 2 by equation 1.